Hello everyone. Let's start solving the last set of the 2021 CSIR question paper. Okay, I think it was June. Yeah, June question paper, and we are doing only the organic questions. So last 31 to 35 questions, 5 questions we'll be doing. So the first question says the correct relationship between two faces of C double bond O group in compound A and B is. So these are the two compounds. Asking for A, tell what is it, and for B, what is it. They are two separate questions. Okay. So options are diastereotopic and anisotropic, both are anisotropic, anisotropic diastereotopic, or both are diastereotopic. First, let's understand what is this topic. What is this topicity? Okay. So basically, it is to recognize how two hydrogens will behave in NMR spectrum in a same molecule. So many times we think that two protons are equivalent, something like this. If two hydrogens are here, so we think that both hydrogens will come as one peak, but many times they are not. They will come as different peak. So to understand this, we use term what is called as homotopic, anisotropic, and diastereotopic. So here we'll be doing only about diastereotopic and anisotropic because that's what is being concerned here. Homotopic is basically they are the same molecules or same hydrogens. Okay, let's first understand what is anisotropic. So imagine take this molecule butane. Okay, now it has two hydrogens. Now if I change one hydrogen with some other substituent, okay, I put Br, that let it be one molecule, and I change this hydrogen with other molecule, and this is the other molecule. Now we can see that now this molecule has become chiral because it has four different substituents, and these two will be mirror images, and so there will be pair of enantiomers. So these two hydrogens will be called enantiotopic. But you know, enantiomers, they don't show difference in NMR peak, so they both will come as same. They will show same single peak in NMR. So this is what is called as enantiotopic. So what it says is it can be easily identified when molecule has no chiral center and just one prochiral center, whose replacement of a proton with substituent would lead to formation of chiral molecule with just one chiral center. Very important. If more than one chiral center is there, then complexity rises. We know we get 2 number power and stereoisomers, right? If only one is there, that means 2 to the power 1, that is 2. 2 stereoisomers are there. The only possibility of this 2 will be enantiomers. Okay. Now what is diastereotopic? Now it is very clear. So if two hydrogens are there, if we change one hydrogen, then we should get diastereomers. How is it possible? It is often possible like when you have molecule which has one another chiral center, but that's not always the case. Sometimes it is being developed, but this is simple case, so let's understand with only that. Something like this molecule, you are having 2s bromobutane. Now this chiral center is fixed, and we have to find out between these two hydrogens. Okay, we have to find out the topicity between these two hydrogens. So what do? We'll change hydrogen first case and we put bromine here, and we do another molecule, we change this hydrogen and draw another bromine here, and we have to find out relation between them. Is it very clear? So what happens? This part has not changed, so that means this part remains superimposable on each other. But what happened? This part is not superimposable because you can see bromine is towards the viewer, this is away from the viewer. So basically it is like these two parts will be mirror images. So overall what has happened? The molecule is neither mirror image nor they are superimposable on each other. That means they are diastereomers. So these two hydrogens are diastereotopic in nature. So now we know diastereotopic means diastereomers, diastereomeric hydrogen shows different NMR peaks. So that means these two hydrogens will show different NMR peak in the proton NMR. Okay, you can see also very clearly this hydrogen gets more influenced with bromine because they both are on same side. More or whatever it is, but yeah, this will get influenced differently with this bromine and this hydrogen gets differently with this bromine because this bromine is 180 degrees from this bromine. This hydrogen is 180 degrees with respect to this bromine, and these two have yeah, some amount of difference will be there, some angle, but that's not 180 degrees for sure. Okay, so these are called as diastopic protons, and they will show difference in your proton NMR. Now it is asking for these molecules. Now it is asking for these molecules. What is the topicity? What is the topicity on the two faces? That means, see, it's a planar. C double bond O means it's triangular planar in shape. So that means one face is this side, second face is this side. So let us discuss this question separately. So when you come here, let us explain, understand this. Let us put two functional groups, okay? So one side will put OH, other side hydrogen, and here we are changing it like how we did for previous one. Now what happens? Very clearly, this is a chiral center. You can see here. This also is a chiral center. These two are exo bonds and CH2OMe. These two hydrogens are exo bond, and these two CH2OMe which is down, they are endo bond. So it is already chiral. Now when you are changing this, these two will create, it creates a new chiral center, and these two will be kind of mirror images, and rest part is identical. So overall these two hydrogens are overall the molecule is neither superimposable nor mirror images. That means these two hydrogens are diastopic in nature. Is it very clear? So that means the two faces of this oxygen C double bond O are diastopic in nature in molecule A. Let us look at molecule B. Here what happens, you see this molecule actually is meso compound. There is a mirror image here, though this thing looks like it is chiral, but it's not chiral. Wherever you go, you will come across the same face. So it is achiral. So if you change and you get H and OH and OH and H, you will get pair of enantiomers. That means these two are enantiotopic. These two hydrogens are enantiotopic because no more chiral center is there. Only one new chiral center is being developed. Somehow it didn't come out very properly. This yeah, this OH I should have drawn like that. Okay, something like this. OH I should have drawn here like that, and here hydrogen I should have drawn something like this, so that it becomes more clear. Yeah, but pretty much that's the case. So these two are enantiotopic. So the two faces of C double bond O in molecule A is diastotopic, and for molecule B is enantiotopic. Thus the answer is option number A. So whatever I said I have written very clearly. I'll go down slowly. Please read it carefully, okay? Please pause it in between and keep reading it. It's important topic. Once you understand, it's very easy. Otherwise it always creates problem. Yeah, moving on to the next question, question number 32. It says a compound shows M plus at M by Z 84. So this is molecular ion peak, okay? And the base peak, that means after breaking up somewhere it forms some ion which is more stable than the molecular ion peak, okay? That is coming at 56. It exhibits only one single peak in proton NMR at 1.4 ppm. It's quite low, okay? And one signal in 13 CNMR also it is showing only one peak at 35 ppm, delta 35 ppm. So the compound is asking, is it cyclobutane, 1,3-dione, dichloromethane, cyclohexane, or 1,2,3 dimethyl trimethyl cyclopropane. So let's draw. So option A was this, right? Now this molecule you can see very clearly, this carbon and this carbon are identical, and this carbon and this carbon are identical. That means we should get 2 peaks in carbon 13 NMR. So we can forget this. Let's move ahead. This one looks alright because only one carbon is there and these 2 hydrogens are identical. The only thing is 2 chlorines are attached to this carbon. So it will de-shield because chlorine is electronegative. So it should come much higher, cannot come 1.4. Actually I looked into it, I drew it on camera and saw it will come around 5. Okay. So that's not the right answer. This molecule, now this is chiral because every center is having different hydrogens. So we talked about topicity. These hydrogens are diisotopic. So they will show different NMR peaks, proton NMR. So D also cannot be the answer. Answer will be option C. Option C, you know, they stay in cyclohexane form and they keep flipping. So we can think that no, axial and equatorial should show difference, but it's 50-50%. So all hydrogens are identical. It will show very clearly just one peak. Okay, it will clearly show only one peak. And apart from that, what happens? All the carbons are identical because all are same CH2 attached to each other. So they will show single peak in both proton NMR and carbon 13 NMR. If you calculate, the mass also is coming to 84 because 6 carbons are there, so 12 6 is 72 plus 12 carbons are there, as 12 hydrogens are there, so it becomes 84. Now what happens? Base peak. So it undergoes splitting like this. You can see here, this will break up as alkene and this forms unstable cyclobutane structure. This comes to 56. That is what is coming as base peak. Okay. So that's it. The answer is option C. Moving on to the next question. Question number 33. The reaction that will show a large increase in rate when the reaction medium is changed from non-polar to polar organic solvent. So it is saying you are changing from non-polar to polar, which will show maximum rate of increase, maximum increase in rate of reaction. So what happens? Basically it says if your product is becoming more polar than your reactant, then what happens? Then if you change solvent from non-polar to polar, reaction becomes very fast because it will stabilize your products, and therefore reactant will be forced to undergo reaction faster. Apart from that, if it is polar, if your product is polar, your transition state also will be polar, and therefore it will be stabilized in polar organic solvent, and thus reaction will be fast. Okay, so yeah, you can read all this, whatever I said is written here. So I put some effort and I found out this. These are the nice images I got, and I have made it here for you all. So if your reactant is non-polar and product is non-polar, so you get simple peak, but you will not get any extra stabilization if you change from solvent from non-polar to polar, because this transition state also will be non-polar. So it have quite high activation energy, right? Now when your reactant is also polar, product is also polar, so again you are getting stability. That's why this reaction is occurring. You are having little low, but of course this transition state will be still high because nothing much is happening. As much as the solvent was stabilizing a reactant, that much it is stabilizing the product also. So it doesn't affect the transition state energy much. But what happens when you are having non-polar reactant and polar product? Now when you are having transition state which is polar, now when you are having polar solvent, it stabilizes it, and therefore this height is much lower, you see, because it is stable, whereas product will be very stable, it will be much down, and therefore it will be high. Reaction will be very fast if it changes from reaction changes from non-polar solvent to polar solvent. And if reactant is polar and product is non-polar, of course reactant will not be fast because product is less stable. Okay, this it will not stabilize the transition state. So let us look at the species. I'm so sorry. Yeah, here what happens is pretty much both reactant and product have same polarity because charged species are more polar, we know that. So here also one molecule is polar, another molecule is polar. So pretty much same, so you will not get that kind of stabilization. Here it is opposite because this is more polar and these are less polar. So definitely this also cannot be the answer. And here also is pretty much same, but here we can see very clearly non-polar is giving rise to very polar because it is charged species, and therefore reaction will go faster for option D. Next question. The major product formed in the following reaction is. Whenever you see some question like this where boron is there, okay, and you see transition element, please understand this is Suzuki coupling, and it's very simple actually. You have to just think from where boron will attach. So you know boron will attach from this side, and then what happens is just you have to, this is boron, and yeah, and then you see PHBr, so just cleave it and attach of Br. So it's reaction, this reaction Suzuki, Komada, all these are used for alkylation or phenyl, addition of phenyl group on all these groups, that is vinyl position or yeah, vinyl and phenyl groups, where we cannot do by simple SN1 and SN2 reactions. Okay, let us see the mechanism how it happens. So the first step is of course 9-BBN. 9-BBN, you know, very bulky boranes. So of course it will not choose this because this is more hindered than this one. So it will attack in the less hindered side and you get something like this. Now very clearly we know boron will not attach on this carbon. It is first this alkene acts as nucleophile, boron acts as electrophile. So if it comes from here, you get positive charge on second carbon. This is secondary carbocation. Had it happened other way around, this is very important concept, I hope everybody knows this. Had it attacked other way, then what happens? You are getting a primary carbocation. Now primary carbocation not stable, everybody knows that, correct? Carbocation means electron density is less, it is electron deficient. So when it is secondary, two sides alkyl groups are there to pump electron, stabilizes this, and therefore secondary carbocation is more important than your more stable than your primary, and therefore it attacks like this and you get this, and then hydrogen gets attached and you get this. So very clearly allyl group, this double bond has gone off. Now second step, what happens? You are adding PDPPS34, sorry, I'm so sorry, PDPPS34, and then you are adding PHBr. So when you are having PDPPS34, this is 18 electrons, so it is not reactive. So it is PD0, so it undergoes oxidative addition reaction and it becomes PD0, 16 electrons. It is much more reactive now. So basically two ligands are lost, 2 PPS3 is lost, and PHBr breaks up and gets added. Now this is like Grignard reagent. Because palladium is metal, it is electropositive, so this is positive and phenyl is having negative polarity. Okay, phenyl is having negative polarity. Now what happens? Now this has to go and attack on the palladium so that Br leaves. But carbon does not have negative polarity. Something like if you have RLI, then because lithium is electropositive, so carbon has electronegativity, so it is very nucleophilic, sigma bond is nucleophilic. But here it is attached to boron. Boron is not electro positive like lithium. Okay, so this cannot go and attack here. So that's why Suzuki coupling, we always add base. K3PO4 is being added. So when you add K3PO4, PO4 gets added here. So when you add PO4, you get negative charge on boron. Now it has become boronate. Very important. Please understand this concept is very important. Once the boron gets negative charge, all the bonds of boron are nucleophilic, they get negative charge. So this sigma bond becomes nucleophilic. It will be able to attack this negative charge, and this sigma bond becomes nucleophilic. This sigma bond will be able to attack this palladium, and this Br leaves, and you are getting this species. Then what happens? Now we know that pH is having negative polarity, so this goes and attacks here, this leaves, and you are getting coupling reaction. Thus your answer is option number A. This is very important. A lot of concepts came in this one question. I will go through it once again. Like I will just go up to down slowly. Please read it again. Yeah, so this is the question. Please read it slowly. Pause it as you want. Yeah, last question for this question paper. The major product in the following reaction is, so we are having diols basically, and 1 2 1 3 diols kind of stuff, and you are adding benzaldehyde. So of course we know this will form acetal, and adding H plus, it is asking which will be the product formed. So this is an interesting question. If you do little bit also of carbohydrate chemistry, you will be using lot of this stuff. So one very important point is, for acetal formation, if it is 1,2 diol, both the diols have to be cis to each other. Now this is not drawn very properly. Actually asked somebody else to draw, so it was not proper. This OH should have been like that. So what happens, you can see here H is up, axial position, this OH in equatorial position. Here also H is down, OH is up. This is axial hydrogen and OH is in equatorial. Now this OH is below the plane, this OH is above the plane, so they are trans to each other. So if you try to do this acetal protection, it will not occur. Please pay a lot of attention. So if 1,2 diol has to be there, they have to be cis to each other. So if this OH was on top as it is seen here, this OH should have been on top. Then this reaction would have happily occurred if this was hydrogen and not OH. So that this OH is above the plane because this hydrogen is down, and this OH is also above the plane, so they both will form. Okay, so this is the important concept. So if you look here, yeah, this will happily undergo acetal formation because this OH is above the plane, this OH is above the plane, this will occur. And tertiary butyl I have shown because it locks the ring, it will not allow it to flip. Yeah, but what happens here, see here, this is below the plane and this one is above the plane. Hydrogen is down, CH2OH. But here this concept does not come because not 1,2 diol, it is 1,3 diol. So it forms a 6-membered ring. So it forms, this is called as benzylidene protection. We use a lot in carbohydrate chemistry to protect OH at carbon 4 and OH at carbon 6. So what happens is, yeah, so this is very stable, and important part is this pH. See, there is a hydrogen also here. So hydrogen is small, it occupies axial position, and pH occupies equatorial position, which is more stable. Okay, equatorial position is statically less hindered. Now let us look at our question. So our question is this. So it will have two transition states. It will have two conformers. So this OH is towards the viewer, so I am drawing it above the plane. This CH2OH is towards the viewer, so again I am drawing it above the plane. This OH is away from the viewer, so I am drawing it below the plane. Okay, so H is on top, OH is bottom, and similarly here OH is below the plane, so CH2OH is above the plane, and here OH is above the plane, H is below the plane. So in planar structure, whatever is towards the viewer, please draw it above the plane. Whatever is below the plane, please draw it away from, whatever is away from the viewer, please draw it below the plane. Okay, so hydrogen above the plane, OH is below the plane because OH is away from the viewer. Now it flips. So once it flips, what happens? uh, this all the axial position becomes equatorial and all the equatorial becomes axial. So you are having this OH from axial it went to equatorial, this CH2OH from equatorial became axial, and this OH from equatorial become axial. Now between 1 and 2, of course 1 is more stable, because here two bulky bonds are in equatorial position and only one bulky bond is in two bulky bonds are in equatorial position and only one bulky OH group is in axial position. Whereas if you look here two bulky groups are in axial position and only one bond is in equatorial position. So basically we have to think from this conformer and we have to get our answer. So now two possibilities are there. One is this is there. So of course this is 1, 2, 3. At position 3 you are having. So this can undergo benzylidene formation, because though they are trans, we saw that when it is 1, 3, so it forms 6 membered ring, it is possible. Also it is possible that it can form this 1, 2, 3. So here 1, 2, 3, it can form like this. But this is very unstable. This is cis-decalene, whereas this is trans-decalene. So it will form benzylidene on these two, 1, 2 rather than 1 and 3. Okay, rather than 1 and 3. And very clearly we told also that this pH will not be in axial position. Here simply I have put this thing so that clarity is not there right now. We will try to understand, but basically it will remain in equatorial position, it will not go in axial position. Okay, so this is what will be there and not this. So now when we draw the product, what we'll draw? We'll draw OH above the plane and pH below the plane. Sorry, OH is above the plane, so when we draw the planar structure, we'll draw OH towards the viewer, and pH is below the plane. You can see H is above the plane, so pH is below the plane, so we'll be drawing pH away from the viewer. So once you draw this, see this pH is away from the viewer and this OH is towards the viewer. Thus your answer is option number C. Okay, thank you very much.